My name is Davila. I'm the principal security researcher for Pumabot Networks, mainly working on IoT and OT vulnerabilities and malware research. I've presented at multiple conferences, including like DEFCON, RSA, S4, and you can find me everywhere as Asher_Davila.
Hello, everyone. My name is Chris Navarrete. I am a senior principal security researcher working for Pumabot Networks. I focus on the detection engineering, especially in C2 frameworks, malware, and I am part of the advanced threat prevention team. So everything about Cobalt Strike, anything like that. So I'm pretty much the owner of that. Previously, I have presented at Black Hat Asia briefings and the Black Hat US Arsenal and some other conference as well. So you have the link in here if you want to connect to. All right, so first of all, let's introduce the Golang. So Golang was designed by Robert Griesemer, Rob Pike, and Ken Thompson in 2007. It was firstly publicly released in November of 2009. And then some people knows about this, about the name is Go or Golang. So Go is actually the official programming language, but many people refer to it as Golang. So Golang is going to be easier in the case that you want to see more about the programming language, like for example, searching the actual Google search, for example. All right, so why Go malware? So why is the interest of malware writers using this programming language? So first of all, this is a cross-platform language. That means that we have support up to 16 operating systems. Also, we have the binaries that are statically compiled by default. That means that obviously we will be dealing with larger binaries. So these binaries can also be dynamically linked in the case that you are using the CGO implementation. Also, Go produces self-contained binaries. So this is going to be good in terms of, for example, if you are a malware writer and then you are working on these kind of projects using the Go language, so you will have a really huge binaries. That means that for static analyzers, it will be really difficult to deal with these kind of examples. Also, you will find less dependence of external libraries. So it's going to be somehow good as well. So finally, it is harder to analyze and reverse compared with some other programming languages like C or C++. So Go-based malware in the news. So as you can see here on this slide, so we have different companies with some of the research that they have done. So in our case, for Unit 42, we have the blog post related to the Go brute forcer. This is a Go-based botnet. So it's actively harvesting web servers. And also we have some other companies reporting GovRat, for example, malware, which is targeting Linux routers. And also some other companies like, for example, Go-based Trojans as well. So as you can see here, also some other companies that are mentioning, the malware created in Go is a trend and is here to stay. So let's find out. So we run some internal telemetry, and then we gathered some information, almost like a year, and then we started to find some trends here. So we identified that a peak happening in February and March 2025, and we found different samples related to the botnet malware, coin miners, and sleeper implants as well. Other Go-based malware, we can see here in this table, so we have different malware families. The first one is Sevocry Go. So the purpose of this is just performing a recon, an exfiltration implant. This is being used by the APT24 team, and the binary type is a Windows PE file. Also, we have the second place, the Go tier, which is a wiper ransomware, which is also in the binary type of Windows PE. The third case, we have a Pumabot. The Pumabot is just a malware which focuses on attacking IoT devices, and it performs different malicious attacks, like for example, SSH brute force. This is a Linux ELF sample. And also, finally, we have the Botnet Go, which is an IoT scanner and exploiter. And also, this is an ELF for Linux. In July 2024, we have also the first malware, which is ICS-centric. This is called FrostyGoop. So this particular malware is attacking Modbus protocol. And also it was, obviously, as you can infer, programming in Go. It was used against the Ukraine in order to disrupt the critical infrastructure. So back then, Asher and I, we did a specific research just to see what is going on about this kind of frosty cube. And then we identified something new, which is actually a new artifact, which is called Go Encrypt. And this is a secondary tool or an artifact that apparently they are using to encrypt and decrypt configuration files that are based in JSON. So if you want to know more, we also included the QR code here if you want to see the deep analysis on this. All right, so the programs analysis challenges for Go. So first of all, we have the large file size. So as I mentioned earlier, so this is going to be really good in case that you want to evade, for example, security scanners because of the file limitations. So this is actually true because we try different kind of cases, and if you have like really large files, the static analyzer is saying, well, I use abort mission and I don't go further, so it's bad, right? The second thing is about the analysis complexity. So we know that for these Go binaries, we see a high function count. And obviously, this is because of the static linking. If you deal with malware before, you will see that when you're dealing with a lot of functions, it's going to be really difficult for you to figure out what is going on. So this is also making really difficult. The third one that I have is the tooling limitation. So right now, most of the reverse engineering tools are designed to support C and C++ binaries. So obviously, in order to deal with the Go's unique characteristics, so we just need to know which kind of tools we can use to fulfill the requirement here. Finally, we have the string handling. So unlike C and C++, we will see that you pretty much dealing with strings that are null terminated. So in strings, we have a specific structure, which is counting the byte elements of the array. And also we have at the same time the length of the byte array. So in this case, so we are dealing with two different things at the same time. So for the tooling for Go analysis, so we have the disassemblers and the compilers. So we have R2, we have Jira, we have Binary Ninja, and on top of it, we can also use some other, for example, AI-assisted tools. So you can have R2 AI, we have R2 MCP, Jira MCP, Sidekick, and also you have additional tools like, for example, Go Strings, Go Resim, and Redress in order that you want to deal with some more complicated cases. All right.
Yep. All right, so let's go to the section that says main difference, Go versus C. And you can see the first thing we tried to compare were two very similar programs, so just a hello world kind of a thing. So it says hello DEFCON. It has the Go version on the left and the C version on the right. So you can see that they're very similar programs. But when we go to the next slide and see the sizes are a huge difference, right? So for C, you can see the binary is 16K, but for the Go, it's 2.2 megabytes. So it's huge, just for a simple program of a hello world style. In the next slide, we can see the binary info. And you can see, again, the sizes are pretty different. Some of the compilers, most of the time you're going to see that the Go binaries are mostly statically linked. And when they are dynamically linked, it's just because of some special scenario that I'm going to describe later on. In the next slide, if we see the string search, you're going to see the strings are one of the things that are behave completely different from Go than C. So in Go, you see the first image, or the first part of the image is a C representation of the string. So you have a null terminator. So tools like strings can immediately identify when the string ends. So when it finds the null terminator, it says, okay, this is the end of the string. But in Go, that's not the case. You can see that there's a chunk of garbage and a lot of strings all together. And the reason is because the way they behave is very different in Go. They don't have null terminated strings. In the next slide, you can see the number of functions. So we listed the number of functions of the program, of the same program, and the Go has 1,800 functions, and C only 10. And in the next slide, if you see the disassembly is pretty much similar, not much change, but immediately you can see that there's a lot of much more code on the assembly side of Go than C, right? It initializes a lot of the routines, runtime things, and it creates a lot of I would say for analysis, some garbage code. And in the next slide, we can see the decompiler view. The way we decompile this was using PDG, which is a decompiler of Ghidra that is embedded within Radare 2. And we try to use most of a lot of open source tools for the entire of the presentation. So in this one is Radare and Ghidra are tools that go really well together. So you can use the compiler there, and you can see it is integrated. And actually, you don't need to install Ghidra to use Ghidra's decompiler inside of Radare. So in this one, you can see even the decompiler can, with no changes, the C version, you can immediately see that it spits out the code that says hello DEFCON, and in the Ghost version, you cannot immediately tell what is going on. So now let's go to the sections. And as many other binaries, you can see that they have sections, right? But the sections in Go binaries are kind of different, or you're gonna find different kinds of sections, like for example, Go build. So Go build info section is a section that is found on all the Go binaries that are either ELF or Mako. In PE files, they are in a different section, so you're not going to see it immediately there in the parsing of the sections. You're going to need to find it within the binary, in the data sections. And then if it is compiled with Go mode, which is enabled by default, you're going to have a lot more information available. So by default, you're going to have way more information than a strip C binary. And then we can see in the next slide that you can see the magic number of the section, and you can find a lot of interesting things as a reverser is going to be very useful, like the Go version. Go version is very important because depending on the Go version, the magic numbers are going to be different. You can see the Go build info. So there are many things that are going to stand out, and you can quickly identify if this is a Go binary or not. Right? It also tells you the architecture. Like in this case, it's an AMD 64. And the operating system is a Linux machine. Right? It was compiled on a Linux machine. And also, it tells you some of the command line arguments that were used during the compilation. Of course, they are not all of them explicitly stated, but are the ones that your configuration of the build executed to compile the binary. Then we have the Go PC line table, and that table is very important because it's going to act as a map. And that map is going to help the reverser to reconstruct the binary, because in that section, it's going to be, you're going to have them, if you go to the next slide in which there's an image that says magic number of the Go PC link table, well, that magic number is what many tools use to identify and try to recover or reconstruct the binary. And that magic number, be very careful if you're trying to do your own scripts, because that magic number changes depending on the version of the Go binary or the Go compiler that you use. So it is not always F1, FF. So just be careful about that, because when I was building this script for this, we're like, hey, why it works for some binaries, it doesn't work for some other binaries, and the reason is that magic number changes. So, and then you can see in the left side, in orange, the storing memory addresses. Those are the pointers to they call them the program counter. So they are mapped directly to each of the lines on the assembly representation. And then you can see on the right side, those are the pointers to the metadata of each functions that are in the table. And then also you have things like the size of the function symbol table. And all of those things are going to be very important if you're building a tool that wants to parse this. And actually, this is the most important thing that I want you to take home, is this part for my side. So it's like, if you have a binary that looks very weird, that your tools are not working, don't be afraid of that. Just read the documentation, try to see how the binary or the file that you're trying to parse is made of, and those magic numbers, how is it being parsed, is gonna be the key to help you to understand and parse and try to analyze the binary you're looking at. And in the next image, you see the struct function, and the struct func, there's the link of the official documentation of Go, and in which you can see that it has a uint pointer, which is the start of the function, and also you have the name. And that's going to be very useful to try to reconstruct the binary with that information, right? So in your script, you're gonna parse what we mentioned in the last slide, and you're gonna use that information to rename it in your tool. And then I'm gonna mention some tooling. As I said, there's a slide set that says tooling. So from there, I try to use mostly only open source tools. We try to use mostly open source tools. Of course, I had to introduce some commercial ones. I know that you're open source enthusiasts and you love open source. I'm sorry. I hope I don't offend you. I try to not put any brands, just that Coca-Cola there. But other than that, I hope everything that is open source, anyone can do it at home. And in that part, you can see that there are two types of string handling. One that is dynamically allocated, so it means that during runtime it is going to be try to reconstructing the string, and also you have statically allocated, which are already there, but they are just a huge chunk of chars that are not clearly defined, for at least for the tools, of course. And even if you go to the next slide, when you say Ghidra, it says it supports a Golang compiler. So even if you choose that option, when you try to open them, you're going to see that there are some caveats that it still doesn't completely construct a binary, especially for the string side. So the NCC group, very famous guys, they did this GoStrings feature, or it's like a plugin that you can install on Ghidra, for example, and they propose a flow. So they give you 8 steps. Some of them are optional, as you can see there. But if you can see in the next image, I try to run in that order that they suggest. And in the image that says before and after running GoStrings, you can see in the left, even though I already selected the Go compiler option in Ghidra, it's still, there are some strings that are not found, right? It is the same program that we've been analyzing. So in the right side, we see that after running the scripts in that order, then you can see the word defcon, right? And hello defcon, and it's well defined. But also wanted to give something new, right? Something more, because many people have already talked about this, like how to, the problems of analyzing Go. But we wanted to do something more like something that is in the news, try to use AI. Of course, it's not everything about AI. Please don't think about that. I want to try to explain different things, and it's not about that AI is going to solve all the problems, right? It is just going to be it's going to act like a Clippy. R2 AI actually is defined as a kind of like a Clippy that you remember that you were back in the day using Word, trying to write a love letter and say, oh, looks like you're trying to write a love letter. Do you want me to help you? So it's going to be like that. Like it's going to suggest you some commands, because Radar, if you haven't used it, is a low-level tool that it compared to other decompilers, it doesn't start loading, and even as a debugger, it doesn't start at the main function. It starts at the entry point, and not even at the entry point. Sorry, at the loader. So why? Because imagine you are trying to debug a vulnerability that happens at loading time and when the binary is loading, and you already skip that part until the entry point, you already miss that part. So that's why certain tools like this start at the very beginning and not at the entry point. So this is what they do, and they use mnemonics. So instead of commands, you supply mnemonics, and that's why it is very difficult to, if you haven't used the tool, if you haven't read the documentation, it's very hard to use it. So this tool is going to help you to ask questions to the tool, like, hey, how do I open this function, or how can I know the strings contained within this section? So that Clippy is going to help you to answer those questions on how to use the tool without having to read the entire documentation. And then we use some commands that you can use to install, and how to set it up, right? It has so many different use cases. You can use it as an assistant, as a decompiler, as a crack me solver, as a CTF. So out of the box, it can help you for a lot of things, but for more complex things, it's not like the solution for everything. It is not gonna steal our jobs. So it's just gonna be a sidekick for us. It's just gonna be someone that is gonna be there for us to help us when you feel lonely, but it's actually not gonna replace you. And then I just put some slides on how to set it up in case you want to try it at home. You need to define an API. So if you can use a commercial one, you can use your own models that you have trained. You have a local model, you have a server running with your model, you can use it. You just need to define the provider, which they call the API, and then you need to define the model, In this case, for the first example, we used Gemini as a provider, and we used Gemini 2.5 Pro for the model. And it's very confusing. Everything in Radar is very confusing in terms of naming, but R2 AI is actually a model that has different modules, or it's a component that has different modules. And R2 AI has a module called R2 AI, but it also has another module called DK. And that DK is gonna be another way to decompile it. So as you know, Radar has like different ways to decompile. Like you can use like the Ghidra decompiler, but you can also use this new way to decompile binaries, which is you're gonna ask the LLM to try to decompile it or translate the assembly into source or as close as possible as source code, right? But the cool thing about it is that you don't need to supply exactly assembly, because I know very models are not very well trained in assembly, so you can pass intermediate representation. So Radar by default has ESIL, which is the intermediate representation, but you can use other intermediate representations that you can pass to the models, and it can tell you and try to decompile the best it can. And for example, after the R2 AI modes, there's a slide that I'm asking a question. It says R2 AI minus A. And I asked the question, in what language was this program developed? So it suggests me, it is not, by the way, this is not fully automated. It just suggests me the commands that I should execute. So you can see it suggests me to execute AAA, which is full analysis of the binary. It suggests me to analyze the information of the binary. And it also suggests me to print all the functions from the binary. And then there is the output of those commands are going to be fed in. They were fed into the model, and then it answered with in the slide that says R2 AI assistant response. The assistant responded based on analysis of the binary. It's clear that this program was developed in Go. So several pieces of evidence point to that this is Go, because we found like this and those strings that clearly tells us that it's a Go, right? In this case, it says that it found the function fmt fprintline and some other garbage functions like for panic messages that indicates that it's a Go binary. And then we try to use DK. As you can see, in DK you can set up different models and different ways to decompile it. In my case was like just make it as possible to look like C. And then it clearly did, right? It's decompiled into, it also gave me some context and the output that is predicting. And it says, okay, the conclusion is that this program is printing hell of DEFCON to standard output. But also we use this MCP approach. It also, you can use whatever provider that you want. In this case, we use Claude for the agent, for the MCP agent, connecting to Radar. And in this case, this is fully automated. So if you follow through the slides, there's one slide that says automating the task. And then I ask a simple question. I said, disassemble the binary. I pass the path to the binary in my computer, in my laptop, like locally. And then I say, tell me what the program is doing. So it tries to disassemble, and here I don't have to interact with it. In the other one, it suggests me commands. I had to click enter, and I can modify the commands if I say, okay, this doesn't make too much sense. But in this case, it's fully automated, and it tells me key assembly analysis, like binary characteristics, and finally, the expected output.
All right, now that we know a little bit more about the Go, so let's go delve into the malware. So let's identify what's going on with Botnet Go IoT malware. So let's have some kind of introduction about the threat. So it was first discovered in 2021. It targets IoT devices, and also we have seen that a lot of vendors are part of this. So this malware performs scans and exploits more than 30 vulnerabilities, and also sets backdoors on open exploitation and compromised machines. Also a listing of commands and drops additional shells. Also, we have added here the SHA-256 of the sample in case that you want to play with it. So this is a Go ELF 64-bit dynamically linked and unstripped binary as well. So we will look at the virus total information. You will see that there's a 41 out of the 66 vendors identified as malicious. And also there's a CVE that I highlighted over here. So when we run the file command, and we can obviously see the go build ID, which is basically there. And also we use a redress info option just to see what other information. So in this case, we have additional information like compiler version. So you will see a lot of information besides of this. So let's see about CVEs and exploits. So we have a clue, there's at least one. And then when we just try to find exploit for that, we identify that the exploit database has at least one hit. So this one is mentioned in the GPON routers. It's having authentication bypass and command injection. So if we read the description of this CVE, is targeting the Dasan GPON home routers. And then you will see some URIs also included in here. So the next slide is just a little bit of the content of the exploit. So in this case, we just want to do some cross-referencing just to see which actual CVEs are related to the strings that we see here. So in this case, we were able to identify two. And also at the very bottom, you will see that we run the strings command, and then we did a grep just to see, like, for example, the very first string, which is xweb. And then whatever we can find also. So obviously you will see we're getting a lot of information starting from the string that we just look. So how and where are these strings referenced? So we can infer that everything is probably coming from the raw data section. So by using R2, there are different commands that you can display the additional information. So in this case, we use the IZ raw data in order to do a dump of the section and then looking for the same string. So in this case, we use pretty much get the same kind of information, right? So one thing that we need to notice here is that we get the exploit payload, but also a lot of different information, which is mentioning like, or at least giving us a clue that there's some sort of command injection as well. But you will see there's a bunch of suspicious information here. We see HTTP headers, like really, really suspicious, some file names, commands, wget. So it's kind of highly suspicious over here. So the next one is just we run the Gore sim with the human option just to see what is going on. So obviously this tool performs an analysis on the binary, and then we see also the Go version. And also you can see the user functions, the start VA, NVA, the package name, the actual name, function name. In this case, on the right side, you will see survived with all this information. So if you are dealing with this kind of automation, you can use the JSON format, and then you will get this information really properly formatted. In the next slide, we just want to see a quick assessment. We identified that there are several functions. Some of them, the malware author actually mentions the function name as infect. So it's highly suspicious, obviously. So it's interesting to look at. And also, if you see the function names also contains even the vendor. Like for example, infect function Alcatel or D-Link or FiberHome, GPON Fiber, Hongdian, LiveDVR, so vendors. So they are targeting these vendors. It's pretty clear what is the purpose. And also we have supporting functions, like for example, we have the main function, but also we have the reverse shell, we have the scanner init exploit, so highly suspicious. We just want to know what is going on afterwards. So here we use Radare with piping with redress to perform an initial evaluation in the next slide. So we do the mapping, and then we see a lot of information here. Obviously, again, we have the compiler version, and then at the right side, you'll see the redress information. So this one is also giving you additional information about the functions and the number of lines, so where you can get more information about this. In the next slide, we have the GDRA symbol tree. So it's pretty much the same information, a little bit more like visually speaking better. So you will get this information, same one. We see a lot of pretty much the same functions here. The next slide is the strings analysis of a network IOC. So as you can see, we know that something odd is happening. So we just want to make sure what is going on. So we just want to see if we can do a search looking for the GET request or URIs or whatever, and also the post. So what is happening? So on the left side, you see all the GETs, and on the right side, you will see all the posts. So we have a lot plenty of information to dig in. Next slide is a Ghidra exploit payload search. So in this case, we already know what is the string, and then let's use Ghidra just to see what is going on. So we perform a string search, and then we got the match. And in the next slide, we will see the entire thing. So we have step number 1, we got a match. Step number 2, we identify where are the addresses, where these ASCII strings are stored. And then in step number 3, we'll see that address variable. And then we see the function, the referring function, which is the infet function GPON-OG. And then finally, we see, all right, so we identify the address for the function, what is happening next. Usually, when you are dealing with malware, you go and then go to the function, identify the parameters, and do the whatever reverse engineering actions. In this case, we just don't want to do that. Let's use Ghidra MCP. It's kind of new. Let's try it out. All right, so before that, we just want to set up the Ghidra MCP and Claude. So it's quite simple. So you just need to get the Ghidra MCP code from GitHub, and then you just need to install the extension, just to make sure that the configure developer plugins is already there. And also you can configure Claude in order to use a local MCP server. The Python script is already included, so everything is fine. So it's pretty easy. So let's perform a function analysis using Ghidra and Claude. So the very first question is, what is the purpose of that actual function? So we just pass the function address here. So as you can see, there's a lot of information. This is the purpose. What are the different red flags indicating that this is malicious intent? We have different additional clues. Network connections, payload delivery. We have string manipulation, data transformation, memory management, and so on. So in the next slide, we see the network IOCs, and we just want to know what is happening. So we are able to match between the DAT cross-referencing and then the post request, which is obviously part of the strings that we already know. So now that we have this information, I just ask, collect all the DAT addresses related to the particular function and attempt to generate the final payload. So the Claude was saying, okay, so let's analyze it. We have some key findings. We identified the attack method. We have the dot addresses. The AI identified the command injection, even its infrastructure. So command and control, some IPs, host names, target scope. That's pretty much really useful. So in the next slide, we just want to see what about the DAT variable resolution. So even the AI was able to give us some information about the network interface connection data, the HTTP request components, and also the terminator, and also including even the primary attack payload. That means that with all this information, we can somehow reconstruct the actual attack. So in this slide, I also included the data addresses as well. So I asked, okay, so let's reconstruct it, the actual payload. So I got this result. So in the next slide, you will see this is the primary attack vector, this HTTP request, and you will see the actual payload. But something is not right here. So even though that we got something, it's being busybox, wget, something makes somehow sense, but probably not at all. I'm going to explain it further. All right, so now let's reconstruct it. So we just reference it here, the data, and then against the actual local variable in the decompiler. And then I manually somehow created a table in order to identify the parts that are related to these addresses. But if you can see, I see the URL decoded string, which is pretty clear. So it's an IP. It's just requesting the G file, both cases, through the command injection. So in the next slide, I created the final HTTP exploit request header. So, but still something is interesting here. You see the user agent is Mozilla. Mozilla is not WL, so it's kind of odd here. But even though it is going to be used for detection purposes. But also the command injection, as I explained, so this is the URL decoded version, so it's pretty much the same kind of case. So I asked the Claude to provide CVE identification, specifically on the get and post request. And then we got a lot of information, seems to be good, but we just need to investigate further. So I also identify what are the attack vectors found. So for each of the requests, Claude was able to provide a lot of additional information, including CVE. So it's pretty useful, but again, we just need to analyze further. So I just got the post information, and I just trying to identify if it is true or not. So we got CV hits, but also we have true positives and false positives. I just manually checked, so those are not part of the actual attacks, but there are some valid, some invalid, so you just need to be cautious about it. Same kind of case for the HTTP GET. We got a lot of command injections in here. And then we see some offset calculation. So we know that the exploit string is already there, and then we just want to use radar in order to identify. So we got the string, but also the sizes from the listing. And then if you can see on the right side, so we got the exact post, the information based on the addresses and the data sizes as well. So I asked the AI to reconstruct the full script, the exploit script, the POC. But when I noticed is that the main payload was not actually the original one that I was expecting, or the original one that is being used. So instead, it uses a different string, which is odd. So I just manually check, and then the payload is actually Hondian payload, which is a different device. But when I double check, and I even extracted the malware code just to see if everything is right. So I just confirmed that the payload is incorrect here. So we just need to use the GPOG payload instead. All right, so one thing that we can do is also trying to identify unknown functions. For in this case, we have a phone underscore and then the address. So obviously, the AI is able to help you on that. So the to-do list, we need to validate all the payload generated. We need to validate all the CVs. We let the AI analyze additional interesting functions like scanner in exploits. We need to reconstruct all the HTTP requests, and also, if possible, run the sample in a sandbox system. So now let's jump to the Pumabot.
Sure. This is a simple malware. It's also targeting IoT malware, and it's programmed in Go. So let's try to follow the same examples as we did in the Hello World using Radare. So we see the binary info. Well, first we see in virus total that it is identified indeed as malicious. We check the information of the binary using Radare executing I and capital I. It says the language is Go, but it says that it was compiled. When it says that it was, if it was statically compiled or not, it says false. So it means it was not statically compiled. And you say, wait, but you at the beginning said that the binaries in Go are completely statically linked, right? But the problem here, or not the problem, there's certain caveats, is that when you have, there are certain invocations to the C runtime or the C libraries from your computer, it is gonna use something called CGO. And CGO is a way to invoke C functions and linking C libraries from your Go code. So in those cases, that's where you're gonna see that it was not statically compiled. So in those cases, like if some tools are going to struggle with that, and that's why you need to have that in mind. And I promise you, this is one of the last commercial tool that, and these guys were really nice to providing us licenses for Sidekick. And Sidekick, it's a plugin for Binaries Ninja. And then it is going to be, as its name implies, it's just your sidekick, right? It's going to be a small chat in which you can ask small questions. Actually, they recommend you don't ask, like, analyze the entire binary, just certain tasks, like what is this string used for, try to find C2s or those kind of questions. So I try to make a very generic question just to see how it behaves, because this is my first time using it. Like, what are the most important behaviors of the malware? And it tells you that it is using SSH brute force attacks. It tells you the C2 that it is connecting to. It is telling you that it has interesting strings such as Pumatronics, and that is related to a malware family. So even though it was just a very generic question, as an analyzer, and that sometimes you as a malware analyst, you're trying to see if this is a new family, if this is a new malware, if it's just a variant, this immediately is going to tell you what kind of things you are dealing with. So as you can see here, it just tries to ask questions for specific functions that were in the binary. For example, what is the main brute function doing? And it tells you, like, okay, it is enumerating IPs and that is reading from certain URLs, and then it is passing that to try SSH logging function. So I ask, okay, now describe me what try SSH logging is doing. So I, of course, as Chris mentioned, verifying what the output was. And yeah, most of the time, I think it was very precise on what it was mentioning. For example, it says like, okay, it is doing this brute force attack. It does retries, up to 5 retries. And then if it has a success login, it's going to tell you. If not, it goes to the next one, right? And then it tells you, I asked like, hey, what is the C2 domain and what is it connecting to? So it gave me a very, it responded correctly. However, it missed some strings that were important as well. So I went back to the cloud version and just asked, hey, what are the C2s that you can find here? And it gave me the complete list of the domain and where the files that it was trying to retrieve. And finally, well, I asked the question, is this, looks like based on what you already told me and of the reports that we have been gathering, it looks like a Pumabot malware. Is it correct? Is this a Pumabot? Can you confirm it? And it asks, yeah, I can confirm that this is a Pumatronic, or it is a Pumabot variant, and it has a Pumatronics reference of the uname after executing uname command. And basically, Pumatronics is a manufacturer, a Brazilian manufacturer of surveillance systems and traffic camera systems. So yeah, it says likely it's targeting these systems, right? And finally, one of the functions that was really interesting was the system service function. So the last question, I think was the last question, is what is this main function used for? And it tells you that it doesn't tell you that it's being used for evasion or persistence. You can infer that. As I said, it's just a sidekick. So it is telling you that it uses a service file for ready server service. And that is using exec start to create this service, right? And it gives you the path, which is lib redis. But then if you check into the binary, it says that it configures the program, and like if you go and do the manual analysis, you're gonna see that it is doing this, writing this service called MySQI instead of MySQL. This is not an L, it's an capital I. So MySQI service, right? So it is disguising, and it is being used for persistence.
All right, now let's talk about R2 AI versus Goblin EXE. This is our reverse me CTF challenge. So this is a Go, obviously, malware. Well, it's benign, so it is for this purpose, right? It's reverse me. So we have here the GDRA symbol tree. You will see some unknown functions here. We also see the headers. Headers are quite interesting. So it's ninjas don't cry. So that's meaningful name. But also we just ask Cloud to see what is going on. So some key findings, obviously, this is a Packer crypter, some pales in there. So the section names, we already know. And also anti-analysis features, so strip symbols, custom packing, dynamic API loading, uses load library A, good products A. So something is happening here, right? All right, so let's use the R2 AI. So we define the model that we are going to use, and then we start asking questions. So is this binary a reverse engineering CTF style challenge? It is also binary. Try to solve it. It does not contain any plain strings. So we got the guides. So we start typing kind of information, getting information back. And then, obviously, while we are just traversing to this information, you will see the go build ID. So it identifies the AI as a go build ID. It examines further. Let's see what is going on in between. So it says, no, I need to understand where the encrypted packet data starts. So it started looking at the sections. It found the sections, displayed the sections. Interesting, the sections have unusual names. Ninjas don't cry. This confirms it's a custom packed binary. I don't know why. It is an indicator that this is going to be custom. It's just a random name. But yeah, it goes and starts analyzing this kind of next things. It identifies within the sections of version 5.00 LOL. So it starts analyzing. The LOL signature suggests that this may be a custom packed. It analyzes further. Okay, it is attempting to decompress information as well. So it is really trying really hard to see what is going on with this reverse me. So the emulation and debugging, so the AI is really trying hard. So you're trying to see, even though that this is a PV file running on our Linux system, the AI was attempting to emulate and to debug the commands, what is going on. So after all, no luck. So getting stuck. So we got additional information, starting decompressing algorithms, nothing was found. So final result and question. So R2I, 0, Goblin EXE, 1. emulation debugging, so good efforts, but not enough to solve the reverse me. Problems dealing with packers, so what about cryptors, right? I'll be more complicated. So strictly speaking, the reverse me is quite simple, but are we lacking of context here, or what else is required? So if you can beat the AI, let's find out. So we included the QR code in order you want to see the download the sample, and then you can play around.
Yeah, and finally, the key takeaways of this presentation, as I said at the beginning, is don't be afraid of opening irregular file structures. I think that's the core of reverse engineering. Just if what you're trying to open does not match any regular kind of file, just read the documentation or try to understand what it's doing from scratch. And don't be afraid. Like if it doesn't load at the when you're starting doing reverse engineering, you load this into your tool. It doesn't properly loads or parses the information on the file. Doesn't matter. Like don't be afraid of just read the documentation, try to figure out how is the compiler or how the compiler build the binary. Also, what we tried to show here was build a hybrid toolkit, right? So AI is definitely great. It's going to help us. It's going to make us more efficient, but definitely don't rely completely on it, because as you could see, it made mistakes. It doesn't properly identify some things. In the challenge, or the CTF challenge that Chris was describing, it was trying to look for regular compression algorithms, but if the challenge, sometimes if the challenge contains something that is custom made, maybe that's gonna be really struggling for the AI to solve. And yeah.
We just need to, we don't need to take the AI response for granted. So we just need to always validate. Many people, I heard that, you know what, if they are saying yes, just trust. So don't do it. Double check. But even though we can use AI to automate your things, for example, it is very good if you are dealing with a lot of samples every day, not only one, imagine thousands, or I don't know, it's kind of difficult to deal with this. So if we can leverage the AI to do the works for that, it's going to be better. So just filter them out, and then you can just focus on the things that really matters. So this is just a guideline. You don't need to use all the tools that we showed today. So it depends, right? So depending on the requirement, it's the kind of the tools that you will be using, the strategy that you will be using. There's no a specific guideline to do when you're dealing with, malware in this case. So just use whatever you feel comfortable using, and that's pretty much all. So in this slide, we have the QR codes for the IoT enterprise solution that we have, and also the IoT-related research blog post that the Unit 42 had done during this time. So if you want to take a look, so you can go ahead and check. We also included the open source tool links that we discussed today, so you can easily get from GitHub, and then you can play around. And also, if you have any other questions, I think we have still 5 minutes left, so we are open. No? Oh, well, we don't have it, but we can. You have our contact details, so reach out. Thank you.